The goal of this lesson is to introduce mathematics behind neural networks in a simpler, more intuitive manner. In this lesson, let's see what is a neuron in human brain and the relevance to artificial neural networks, then how regression can be extended to a neural network. Then let's understand the building block of a neural network known as the perceptron. Thirdly, we will discuss how to form a neural network, which is also known as multilayer perceptron, what is an activation function, and finally derive backpropagation from the basics. The design of a neural network is inspired by biology, looking at our nervous system. A neuron is a building block of the nervous system which takes different inputs from our sensory organs, process them and produce an output consumed by the brain. On the left hand side, you can see an artist trying to draw the human neural circuit. Resembling this, people have thought of producing artificial neural networks as seen in the example in the right hand side. To understand the necessity for a neural network, let's assume there are two input variables x1 and x2, and we want to relate this linearly to an output y. This will be a plane in the 3D space. For notational convenience, let's use the vector notation and represent this as vector W transpose into vector X. What happens if the relationship is very complex as in the right hand side? This is a nonlinear relationship and simple linear regression won't model the relationship properly. One option would be to apply a nonlinear function f over W transpose into X. Sometimes even a simple function will not be enough to model the complex relationships. So we can combine a set of such functions multiplied by a set of new weights. The same process can be repeated many times as we like, depending on the complexity we want to model. The above process can be represented graphically as shown. We have a set of inputs x, then we apply the function f 3 times to different combinations of the input. Finally, we combine the output of the three functions in different proportions and apply the function f again to get the final output y. This forms a simple neural network. If we consider applying this nonlinear function f to a set of input combinations, it is known as a perceptron. Here we have n inputs starting from x1 to xn, and we add them in different proportions defined by the set of weights w1 to wn, and then applying a nonlinear function f to get the final output y. When many perceptrons are combined together, forming a complex relationship, it is known as a multilayer perceptron or a feed-forward artificial neural network. The inputs to the network are referred to as the input layer. The intermediate layers of perceptrons are known as hidden layers. The final layer of the functions that produces the output is known as the output layer. There are different functions that can be used to model the nonlinearity in the perceptron. Perceptron is also called a node of a neural network. Though it may not be widely used, one option would be to use a step function. It produces 1 if the input is positive or 0 if the input is negative. One of the most widely used activation functions is the sigmoid function. It is also known as the logistic function. When the input increases, the output of this function approaches 1, and when it decreases, it goes to 0. Here, note that the output is greater than 0.5 for positive inputs and less than 0.5 for negative. In the Rayleigh function, also known as the rectified linear unit, the output is the input itself for positive inputs and 0 for negative inputs. This function is mostly used in deep neural networks. There is a variation of the rectified linear unit called the parametric rectified linear unit. As the output, it produces the input itself for positive inputs, and for negative values, it produces an output equals to the input multiplied by a parameter. When this parameter is very small, the output for negative inputs will get closer to 0. When that happens, it is called leaky rel. The reason for having different activation functions and their applications will be discussed in a different lesson. In a neural network, what we have is a hierarchy of nonlinear functions applied to a set of inputs to produce an output. As it is quite complex due to the hierarchy of nonlinear functions applied, simple methods used in linear regression cannot be used directly to solve such a system. One of the algorithms used to solve this problem is called backpropagation, which enables us to use gradient descent on a neural network. Backpropagation gives a way to find the weights of the network layer by layer starting from the output layer. As it solves one layer after the other, we can understand backpropagation if we can understand how weights are updated in one layer. To understand how it works, let's take a single node in the nth layer of the neural network and call it J. In a fully connected neural network, this neuron is connected with all nodes in the immediate input layer, that is layer n-1, and immediate output layer, layer n+1. Let's assume there are C nodes in layer n-1, B nodes in layer n, and A nodes in layer n+1. The nodes in the layer n-1 are connected to layer n through the weight matrix Wn. That means to get the inputs that goes into layer n, you have to multiply xn-1 by Wn. Also, let's assume the nodes in layer n are connected to the layer n+1 through the weight matrix Wn+1. Let the ball face xn-1 represent all nodes in layer n-1, xn nodes in layer n, and xn+1 nodes in layer n+1. Let superscript of elements in weight matrix W represent the element location and subscript the layer number. With this notation, to get the input that goes into node J will be the outputs of nodes in layer n-1 multiplied by the jth row of the weight matrix Wn. As we discussed earlier, when we take node J, the input to that is vector Wj into vector xn-1. Wj is the jth row of the weight matrix Wn. The result is not a vector, it is a single value. Mathematically, this multiplication is known as vector by vector inner product. Let's say there is an error term capital E that represents the output error of the whole system. It is not only related to this node J, but the entire network. In doing backpropagation, one quantity that we are interested in here is how much this error changes if we change the input, that is Wj into xn-1, by a delta amount. That means we are interested in the derivative of E with respect to the weighted sum of the inputs to neuron J. In backpropagation, we are trying to solve the system layer by layer. Let's assume we know the derivatives of the error in the next layer, that is layer n+1. To find the derivatives with respect to the inputs to node J, we somehow have to associate the derivative to the derivatives of the next layer. That is because we are assuming we know those derivatives in the next layer. As the contribution to the error from node J has to propagate to the output through its connections to the next layer, the error should be a function of the values we get in the next layer. This means we can use the chain rule in differentiation to express the derivatives as the sum of the derivatives in the next layer. Here on the left hand side, we have the partial derivative of the error with respect to inputs to neuron J. On the right hand side, we expanded this in terms of partial derivatives of the outputs in the next layer, that is layer n plus 1. Effectively, what we have done is writing the derivative of error with respect to nth layer variable in terms of derivatives in layer n plus 1. The idea is to express the derivative like this is to solve this layer by layer starting from the last layer. We can further simplify this equation. We know that any node in layer n plus 1 takes in all outputs of nth layer, that is xn, multiplied by the corresponding row of the weight matrix wn plus 1 and send that through the activation function f. With the rules of differentiation, each term can be written as the derivative of the activation function multiplied by the derivative of the input to the output node wn plus 1 xn. In this vector by vector multiplication, the only value that depends on xn wn j xn minus 1 is the value corresponding to jth column. Let's see how this simplification comes. Let's look at the weight matrix wn plus 1. If we look at the first output of the layer n plus 1, that is the top node, we can see it is a result of the nodes of the nth layer multiplied by corresponding weights. This is equal to the first row of wn plus 1 multiplied by vector xn. Let's take this first node as an example. Here we can write it as a summation of derivatives as in this equation. When we differentiate individual terms in the summation with respect to wnj xn minus 1, all other terms except the term corresponding to node j becomes 0. This is because we are differentiating with respect to input coming to layer n plus 1 from node j. However, the other terms in the summation do not depend on node j. Because of this, the derivative gets simplified like this. As a result, we can write the derivative of the error at node j as a summation of error derivatives at layer n plus 1. That is dabba re upon dabba xn plus 1 multiplied by some other term corresponding to layer n plus 1. We can further simplify this equation. The derivatives of the error together with the activation function's derivative at layer n plus 1 can be called a new variable delta n plus 1 because it is related to the next layer. As wn plus 1 is a constant, we can take that term out of the derivative. Next, we can write xn in terms of the previous layer outputs multiplied by the weights and the activation function applied. Looking at this equation, we can see that the derivative part is common for all terms in the summation. So we can take that part out. The remaining part we can write as a row vector of weights multiplied by a column vector of delta n plus 1. The equation we have now is only for a node j located somewhere in the layer n. If we repeat this for all nodes, the set of weights corresponding to each node stacks together, forming a matrix. Looking at the previous definition of Wn plus 1, we can see that this matrix will be equal to the transpose of Wn plus 1. The dimensions of Wn plus 1 is a by B matrix and its transpose is a B by A matrix. Delta n plus 1 vector doesn't depend on the node and it is an incremental error passed from the next layer n plus 1. For every node in layer n, delta n plus 1 is a common term. Therefore, it stays as a column vector of size A by B. Multiplication of these two terms produces a vector of size B. Then each term needs to be multiplied by the derivative f dash Wnj xn minus 1. This element-wise product is known as the Hadamard product. It can be represented using this symbol. As the final term, what we get is a row vector of size B corresponding to each node in layer n. In this notation, we have the derivative of f evaluated at matrix multiplication Wn into xn minus 1. This produces a vector. So here, when we are applying the function, we have to note that we are applying the function to each value in this vector. So the derivative has to be evaluated at each point. As we have B nodes in the nth layer, this will produce a vector of size B. This is consistent with the dimensionality of our previous result, because by multiplying Wn plus 1 transpose by delta n plus 1, we obtained a vector of size B. Because of that, we can do the element-wise multiplication. We now have an equation to calculate the derivative of the error with respect to Wn xn minus 1. However, when updating the weights using gradient descent, we need the derivative of the error with respect to Wnjk itself. Let gamma be the learning rate, which is a small constant. We can write the gradient descent equation in this form. To understand how gradient descent works, please refer to our lesson on that. Previous derivative can be easily modified to find E upon Wnjk by applying the chain rule. It just adds an additional term Wnjxn minus 1 by Wnjk. This simplifies to xn minus 1 jk, as it is a quantity that doesn't vary with Wnjk. Here let's summarize how backpropagation works. If we consider an arbitrary node j in layer n, we are targeting in solving for its incoming weights Wnjk. In order to do that, when we use gradient descent, we are interested in finding the derivative of the error with respect to those incoming weights E upon Wnjk. We saw that this derivative depends on a variable delta n plus 1, which can be regarded as the component of the error propagating backwards from the next layer. If we consider layer n plus 1, we can show that delta n plus 1 depends on delta n plus 2 and so forth. With this understanding, what we should know now is what is the derivative if n plus 1 is the last layer or the output layer of the network. In the output layer, we can define the error to be E equals to half of xpi minus xti squared. I is the ith node and xp is the predicted value and xt is the observed value. This is same as the definition of mean square error. In the definition, we have introduced half to get rid of the multiplication factor which comes out when the expression is differentiated. For the notational convenience, let's ignore the superscript I because this is valid for any node. When we take the derivative, we get xp minus xt into dabba xp upon dabba w n plus 1 xn. Further simplifying this term like we did earlier, we get an expression for the error as xp minus xt into the derivative of f wn plus 1 xn by wn plus 1 xn. That is the derivative of the function itself. From this, we can see this is equivalent to the delta n plus 1 for this layer. Starting from this point, we can propagate backwards to update the weights according to the general backpropagation equation and gradient descent. In this lesson, we introduced artificial neural networks as a way of modeling complex relationships between variables. In an artificial neural network, what we are doing is applying a nonlinear function again and again until we reach the required complexity. As the building block of an artificial neural network, we introduced a perceptron. By combining perceptrons, it is possible to build multilayer perceptrons or feed-forward artificial neural networks. The perceptron can have different activation functions, and we discussed those types of activation functions. Finally, we concluded by explaining backpropagation, which is an algorithm used to solve the weights of the neural network using gradient descent. If you think this lesson is helpful, subscribe to our channel for more lessons. If you have any feedback, don't hesitate to leave a comment.